We've seen that definite integrals are a great tool for calculating areas, but they're kind of difficult to work with because calculating the limit of a Riemann sum is very tricky, except in the simplest of examples. So what we're going to do is just try to find some relationships of the definite integral to other things, and hopefully that will give us some more tricks that we can use for calculating definite integrals. One thing that we can do, one new ability that the definite integral gives us is it gives us a new way to build a function, and that's just to let the input of our function be one of the bounds of the definite integral, like this. So we're going to suppose we start with an existing function called f of x, and we're going to build a new function that I'm going to call a because we're going to call this an area function, and it's the definite integral from some fixed spot to x of f. Okay, so let's draw a picture of what this function is actually calculating. So we have here our xy plane, and there's some graph of f here, and we have some fixed spot little a. Now this fixed spot little a could be anywhere, but as soon as you've chosen it, it doesn't move. So little a, you can choose it at the very beginning, but once you've chosen it, it always stays in the same place. Now the upper bound of this integral is some variable spot, which we're going to call x, and we can grab onto this, this spot x and move it to the right or left, depending on what the input to this function is. So the left-hand end of this is fixed, and the right-hand end we can imagine sliding around. Now this definite integral gives us the area under the graph of f and between a and x. So that is this area here. So this region is, the area of this region is the value of our area function, capital A of x. You can see if we slide the value x, if we slide the right-hand edge of this region left or right, the area of the resulting shape changes, and that means that this capital A really is a function of x. The number it produces depends on the x value that you start with. So, so that means that this function really, it does make sense as a function of x. You might wonder why I have a t in here. Oh, I see I have an x here instead of a t. You might wonder why I have a t here, and I should have had a t there. The reason is because, right, we're used to, since f is a function of x, you might expect there to be an x in here instead of a t, but x is our name for the upper bound on this integral. We can't also use it as a variable inside the integral. That's sort of reusing the same name to mean two different things. So we have to use a different variable name. So x is the right-hand end of this region, whereas t is sort of starts at a and passes through every x value in this interval until it gets to x itself. So a is the bottom bound, x is the top bound, t is just sort of a dummy variable that sort of sweeps through all of these x values to accumulate the area, which is what this integral is calculating. If you're familiar with programming languages at all, t is sort of plays the role of an index variable in a loop. That's kind of how it works, right? We could have used some variable other than t, as long as it's not x or a, I guess. So this could be u or b, or I mean whatever you want. I usually use t though. All right, so an area function is given some starting function f of x. The area function, which is this integral, just tells you the area between this fixed spot and x itself. Let's look at an example of this sort of thing. So let's sketch the area function for this particular graph of f of x. Now this area function, I've started it at 0. So we're going to be measuring the area between 0 and the x value that we are at. So let's imagine, well, first of all, I guess we could start at x equals 0. So a of 0 is the integral from 0 to 0 of this function. But remember, the integral from 0 to 0 is 0. So one point on the graph of our area function is 0, 0, right here. As we move to the right, so remember what we're going to do now is treat our upper bound for our area integral as a variable. So right now it starts at 0, but we're going to slide this upper bound to the right. As you slide this upper bound to the right, this function has negative values, right? This area counts as negative because it's below the x-axis. And so as we move to the right, the graph of our area function goes negative because we've accumulated some negative area. As we continue further to the right, we're picking up more and more negative area. So our area function goes more and more negative. As we approach this x-intercept here, we're still picking up negative area, but we're picking up less and less negative area. And when we get to the x value where f has an x-intercept, the area function levels off because it stops picking up negative area. So it must go like this. And it must have a minimum value here because we have picked up as much negative area as we can pick up. All right, now when we continue further to the right, now f starts producing positive values, and that means that this area integral picks up positive area, which cancels some of the previous negative area, and so a of x starts increasing. As we continue moving to the right, we continue picking up positive area until we get to this next x-intercept. When f has this next x-intercept, well, now the area integral stops accumulating positive area, and so it levels off here. When we continue past this x-intercept, now we're accumulating negative area again, so our area function will decrease, like this. So here's a graph of the area function when we started with this original graph for f. Now building whenever we have a new way to build a function, one thing that we have to know about our new method for building a function is how you differentiate it. So our next task is to figure out what is the derivative of one of these area functions.